Okay guys, let's take a look at today's lesson. We're going to be looking at some calculus topics with functions. Basically this is an all calculus lesson. So let's take a look at the first concept, and that is the tangent line. We've actually done this before, but to find the tangent line of a function, what we like to do is use point slope. Yes, my favorite equation of the line. So this little guy right here. And three things, right? We need y1, x1, and m. Those are the three things that we need to fill out our equation of the line. So we first determine the point at which the tangent line touches the graph of the function. So in this particular instance, it would be this point right here. What are the coordinates of that point? Number two, we would find the slope, which is m, by finding the value of the derivative of the function at that point. This is called the point of tangency. And then we would substitute those values into our wonderful, beautiful equation of a line, point slope equation of a line. And so we use the tangent line for quite a few different things. One of the things that we use it for is to approximate the value of the function itself. Let's say we don't know what the equation of this curve is. We have no idea. But we do know that we can find this tangent line equation. Notice how really close to this point of tangency, see the y value of the green line would be pretty close to the y value of that red curve. Very close. The farther away we get, the less accurate our approximation would be. In fact, if we tried to approximate, use this tangent line to approximate a y value of the function, that would be quite, this is a negative y value, that's a positive one. That really wouldn't be a good approximation. But that's one thing that we do use the tangent line for, is to make approximations of the y values. So we use the tangent line, the y value of the tangent line, to make an approximation of the y value of the function. So that's one of our topics for today. We did do some of this, tangent line approximations, last semester with the trig functions. We used a calculator, just total calculator back then, but we basically are, we have a little bit of a different scenario going on here. We're not really working with trig functions. Oh darn right, I love trig functions. But we are still going to use the same kind of technique. We're going to find the equation of the tangent line, and we're going to use it to approximate values of the function. So that's our big topic for the day. So let's go to the next slide and work some examples. We really have two things going on. We have limits and tangent line approximations. So let's kind of look at the limits. Let's take a look at this. So we have a piecewise function, and we're asked to find the limit. And actually, well, not coincidentally, we're finding the limit where that piecewise function breaks, right here at 2. Okay, that's what we're going. We're looking at 2 from the right, 2 from the left, and just actually the full limit at 2. So what could we do? Well, we could graph it, and we could look at the graph and determine what the values are. But what we're going to do today is we're going to work it algebraically. How would we determine this algebraically? One thing that I like to do, just to kind of help me with this kind of topic, is we know that this splits at 2. And so I would write, so to the left of 2 is negative x squared plus 3, and to the right of 2 is x plus 4. Okay, so that's something that I like to note right there. So that kind of helps me as I'm looking through these and deciding, am I coming from the right, am I coming from the left? It kind of helps me right here. So if I'm coming from the right, if I'm coming from this side approaching 2, that's what our first example is. If I'm coming from the right approaching 2, this is the function that I need to be using to calculate my limit. So I'm going to take the 2, and remember, just a reminder, that the answer to a limit is the y value. It's the y value at the location that we're traveling, at our x value location. So I'm going to substitute 2 in, we're coming from the right side. So we would get 2 plus 6, or 8. So I get 8 for that limit. Okay. Actually, it's 2 plus 4. 2 plus 4, and that gives me 6. Okay, so I get 6 for that limit. All right, great. So now let's come from the left. Let's come from the left. So if I'm coming from the left, I'm headed this way, I would use this function, this piece of the piecewise function, to calculate this limit. So let's do that. So we'd have negative, and then I'm going to insert this 2 squared plus 3, which gives us what, a negative 4 plus 3, or negative 1. Now, notice how these two values are different. Coming from the right, I have a 6, and coming from the left, I have a negative 1. That would, basically what we have going on here is at 2, I have the function coming from the right and headed to 6. Now, this I'm just kind of making this up, okay? So it's headed to 6, not the actual function. But we're headed to 6. We're coming here, and it belongs to 2, so something like that. And then coming from the left side, we're headed to negative 1. Okay, we're headed to negative 1. So there is no continuity here. It's not, this particular piecewise function is not continuous at 2. It's showing a huge gap there. So a limit can't exist in a location like this, where we're approaching from the right and we get to one y value, and we approach from the left and we go to a completely different y value. So what we do is we say that the full limit does not exist, but then we have to justify why is that the case. It's part of our answer. We don't just write D and E. The reason is that the limit as x goes to 2 from the right of f of x does not equal the limit as x goes to 2 from the left of f of x. So that's the reason. It's D and E because of this right here. So we need to write this part, showing that those two one-sided limits are not equal. Okay, and that's working with a piecewise function. Now let's look at, yes, one of our favorites, our fantastic step function, the step function. All right, so let's take a look at that. Get some room over here. So in order to work with the step function, if you recall, they're kind of strange little things. They have this, system. Most of them look kind of like that, right? We've seen a bunch of them before. And they have all kinds of discontinuities all over the place. So we really have to be careful. If we're going to 3/2, how do we know that that's not exactly at a place where this is going to be discontinuous? So we could graph it if we want to, but instead what we're going to do is we're going to do it algebraically. How would we do this algebraically? So what I do, I like to do a T-chart. And I basically want to investigate the behavior at 3/2. Now I'm going to actually put that in a decimal form. Just, I prefer fractions, but when we're working with the greatest integer function, it's typically, for me, it's easier to use decimals. So let's just sub this in at 1.5 and see what's going on. So if I put a 1.5 in here, 1.5 plus 1 is 2.5. And what's the greatest integer of 2.5? Yeah, that's right, it's 2. I have to go to the one underneath that, which is so weird that they call it the greatest integer function. But at any rate, that's what they do. So if this is 2.5, the greatest integer of 2.5 is 2. So 2 times 2 would be 4. And that value at 1.5 would be 4. Well, what's happening, let's say, to the left of that? So it's typically safe to go 1/10 away. So we're going to move 1/10 to the left and find out what's going on. So now let's put a 1.4 in here. I put a 1.4 in, and 1.4 plus 1 is 2.4. The greatest integer of 2.4 is 2, and 2 times 2 is 4. Oh, okay, so from the left, it is 4. We're looking pretty good. Now let's look and see what happens as we come from the right. Let's try 1.6. So I put a 1.6 in here. 1.6 plus 1 is 2.6. The greatest integer of 2.6 is 2, and 2 times 2 is 4. Okay, so we are fairly safe. We are comfortable in knowing that this 3/2 does not occur at one of these breaks. It must be somewhere in the middle. So therefore, this limit is 4. It is not. If it occurred at a break, the limit would be does not exist, and we'd have to go through this scenario, showing that the left and the right-sided limit do not equal. But in this particular case, we're good because if we go to the so here's our 1.5, we go to the left, we get a 4, we go to the right, we get a 4, we're good to go. So that limit is 4. When we also do some absolute value graphs. We don't really have to do this kind of scenario with absolute value because absolute value is it's continuous all the time. It's like a V. So we just plug the number in. It's just going to be the y value. We just need to be cautious with piecewise functions because we don't know if they're going to connect at the break. And we need to be careful with the greatest integer function because we don't know if they're asking us for a value at a break. So just some things to be cautious about. All right, let's look at this last example. So we're going to find the tangent line at x equals -1 for that function in example 1. So let's remind ourselves. Okay, so we split it 2. So to the left of 2, we're -x squared plus 3, and to the right of 2, we're x plus 4. Now, if I'm going to want to look at a tangent line at -1, I would need to go to this side. I would need to worry about that side of the, or that piece of the piecewise function to gather that information. So yes, we get to use my favorite equation of the line, y minus y1 equals m times x minus x1. All right, so we have our x1, right? x1 is -1. We got that. We need these other two pieces of information. So how are we going to find our y1? What are we going to do to find our y1? Well, if we have our x1, and I know you've done this lots of times, we're just going to plug x into the proper portion of that piecewise function to get y. And we agree it's over here because it's -1. So f of -1 is going to be negative, and then I plug in a -1 where the x is, plus 3. So we have -1 squared is 1, and then -1 plus 3 is 2. So my y value there is a 2. Okay, great. So I have that piece right there. The last part that I need for my tangent line is the slope. And we have been talking about that before. Slope of the tangent line comes from the derivative. So we need to find the derivative. We need to find the part of the derivative that the -1, x equals -1 belongs to. So f prime, just the piece that we're interested in, the derivative of this, we use our power rule, and we get -2x. Okay, great. So how do we find the slope at a particular point? Well, if we want the slope at an x value of -1, we would simply substitute that in. So f prime of -1 is what we would be doing, and we get -2 times -1, which is 2. So that's our slope. So let's kind of fill in the blanks. So we have y minus 2 equals 2 times x minus a -1 would be plus 1. And there is our tangent line. Okay, so we have our tangent line that we're going to use. Now the last thing they're asking is to use it to approximate f of -1.1. All right, what do we do? Well, what we're going to do, we're going to substitute -1.1 into the tangent line instead of into the function. Now some people are like, well, why would you do that when you have the function? Well, what we're doing is we're just practicing the technique. There will be times where we don't have the function. We don't have it available, we're not able to, to access it. So instead, what we're going to do is we're going to learn how to use the tangent line to approximate it. So let's do that. Let's plug in a -1.1 right here. So we have y minus 2 equals 2 times -1.1 plus 1. So let's continue. Let's just solve for y and see how we're going to go. So -1.1 plus 1 is -0.1, or -1/10. So y is going to be 2, we'll move that over, plus 2 times a -1/10 would be 2/10 or 1/5, -1/5. So we calculate that, that gives us 1 4/5, which if we want it in an improper fraction would be, what, 5 9/5. So our approximation, f of -1.1 would be approximately 9/5. And that's our tangent line approximation. Since -1.1 is pretty close to -1, that's probably a pretty good approximation. If you wanted to on your own to see how good that approximation was, you could actually come back to the original function and put a -1.1 in there and see how close we are. And that is the lesson for today. Are there any questions? All right.